everyone, welcome to my channel. In this video we are going to discuss about rational numbers, Theorem 1.5, which tells us the decimal expansion of a real number is terminating or non-terminating repeating, and we'll also discuss exercise 1.4. Let's get started. In your 9th standard, you have learned about rational numbers, and you know the rational numbers are the numbers which we can write in P upon Q form, where P and Q are co-prime and Q is not equal to 0. We have also discussed that all terminating and non-terminating repeating decimal expansions are also rational numbers. The main focus here is how we can find that the given decimal expansion of P upon Q is terminating or non-terminating, repeating or recurring. For that, we should understand Theorem 1.5, 1.6 and 1.7. So let's get started and discuss all these theorems one by one. First, let's discuss Theorem 1.5. It says that if X is a rational number whose decimal expansion terminates, then X can be expressed in the form P upon Q, where P and Q are co-prime and the prime factorization of Q is of the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. The meaning of this statement is, if we have a decimal expansion which terminates, then we can write that decimal expansion in P upon Q form, and the prime factorization of Q we can write in this form 2 raised to power n and 5 raised to power m. So let me explain this statement to you with an example. So let's take this example. So let this X is equals to 375. We know the decimal expansion is terminating. Decimal expansion is terminating. So it means I can write this number in P upon Q form. Yes, we have learned this also in 9th standard. How we can write 375 divided by 1000. Okay, now see the prime factors of this number. I can split this as 10, 10 and 10. So this will become 2 into 5 into 2 into 5 into 2 into 5. So I can write the prime factors of this number as 2 I have 2 raised to power 3 and 5 also I have 3 times 5 raised to power 3. So in this example, my Q is 1000 and I have expressed this Q in this form 2 raised to power n and multiply by 5 raised to power m, where m and n are non-negative integers. For more clarity, let me take one more example. Let us X is equals to 0.104. This is decimal expansion which is terminating, correct? So I can write this as P upon Q form. So this will become 104 divided by 1000 again. So this is equal to, we have find out this 1000 is, I can write like this. So it means here also my Q was 1000 and I have represented my Q as 2 raised to power n and 5 raised to power m, where m. So here we have 3 in both the cases. So now I think everything is clear about Theorem 1.5. Now let's do Theorem 1.6. And this is the reverse of Theorem 1.5. This says if X is equal to P upon Q be a rational number such that the prime factorization of Q is of the form raised to power n multiply by 5 raised to power m, where m and n are non-negative integers, then X has a decimal expansion that terminates. This is just reverse of Theorem 1.5. So more clarity for this Theorem 1.6, let's take X which we can write in P upon Q form. That's X is equal to 35 divided by 50. Now do the prime factorization for 50. We know we can write 50 as 2 into 5 into 5. So it means 35 divided by 2 raised to power n, 1 and 5 raised to power 2. So here it is given that x we can write in p upon q form, and q we can write 2 raised to power n multiply by 5 raised to power m. So here my n is 1 and m is equal to 2. Then we can directly say that x has a decimal expansion which terminates. You can get a question like find the number of places of decimals after which the decimal expansion terminates. So for that, let me take one example. Let's x is equal to p upon q, and we have write this q in this form, 2 raised to power n and 5 raised to power, and here m and n are non-negative integers. Then two cases arises. Case 1, if n is greater than m, then we can say that the decimal expansion of x terminates after n places of decimals. And case 2, if m is greater than n, then the decimal expansion of x terminates after m places of decimals. Means that we have to take the larger of m and n to find the places of decimal after which the decimal expansion terminates. So let me take this example. Let's take x is equal to 35 divided by 50, and we can write this as this 35 divided by 2 raised to power 1 and 5 raised to power 2. So this means that this decimal expansion will terminates after some time. So suppose we have to find the number of places after which this decimal expansion terminates. So what we have to do, we have to take the larger of m and n. So here m is greater than n, so m is 2. So we can say that this decimal expansion of x will terminate after 2 places. So I think this concept is also clear now. So next theorem, here we have Theorem 1.7. Let x is equal to p upon q be a rational number such that the prime factorization of q is not of the form 2 raised to power n and 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring, we can say. So let's take one example. For example, if I take x is equal to 1 by 3, we know if I divide 1 with 3, I will get first 0 will come and 3, 3, 1, and again this 3 will go on, means this won't, and this 3 will repeat itself. So these type of decimal expansions are known as non-terminating, repeating, and we get these type of decimal expansions when prime factorization of q is not of the form of 2 raised to power n and 5 raised to power m. For example, if I take x is equal to 17 divided by 30, find out the prime factors of 30. So prime factors of 30 are 2 into 3 into 5. So here see we have 3 also. So we are not able to write this denominator in this form. So we can directly say that this decimal expansion is non-terminating, repeating. More clarity about this concept of decimal expansion which are terminating and decimal expansion which are non-terminating, repeating, let's do exercise 1.4. Now let's do exercise 1.4. Here first question is, without actually performing the long division, state whether the following rational number will have a terminating decimal expansion or non-terminating decimal, repeating decimal expansion. So for that we'll use theorem 1.5, 1.6 and 1.7. Let's get started. And so first question here we have x is equals to 13 divided by 3, 1, 2, 5. Now we have to find the prime factors of 3, 1, 2, 5. So let's find out the this will goes with 1 and 5 again. So now let's find the prime factorization of 1, 2, 3, 2, 5. So 5 is here, so it will go with 5, 6 and then 32 and then 5. we know this is equal to 125, and this is equals to 25, and this is 5, and here again 5. So it means I can write this as 5 into 5 into 5 into 5 into 5, which is equal to 5 raised to power 1, 2, 3, 4, 5. Okay, so I can write this as 13 divided by 5 raised to power 5. So here I can add 2 also. 13 divided by 5 raised to power 5 into 2 into 2. I can do like this. Okay, 1 and 1 will come here. So it means I can write my I can write my Q in this form. Q has been written in this form here, 2 raised to power 1 into 5 raised to power 5. So it means here n is 1 and m is equal to 5. So because we have written Q in this form, 2 raised to power 1 and 5 raised to power 5, so it means this decimal expansion is terminating. And after how many decimal it will get terminates? It will get terminates after 5 decimal places. Second question is 17 divided by 8. So here see, we can write this 8 as 2 raised to power 3. So it means here again we can write this 2 raised to power 3 into 5 and 5. Correct. So here also we have written my Q is equal, here also my Q is equal to 2 raised to power 3 into 5 raised to power 1. It means this decimal expansion will terminate. And after how many decimal it will terminate? It will terminate after 3 decimal places. So third question, x is equal to 64 divided by 455. So let's find out the factors of this. So the factors of this will be 5, 9, it will go, means 64 divided by 5 into 91. So see here we have 91. So it means we can't write my Q in 2 raised to power n multiply by 5 raised to power m. So it means this decimal expansion is non-terminating repeating decimal expansion. So next question here we have x is equal to 15 divided by 1600. So let's find the prime factor. Let's find the prime factors of this number Q 1600. So I can write this as 16 into 10 into 10. Okay, we know that this 16 is always we can write like 2 raised to power 4 and 10 2 into 5, and this 10 also 2 into 5. So it means this is 15 divided by 2 raised to power 6 into 5 raised to power 2. So here also I have written my Q in this form, 2 raised to power n and 5 raised to power m. So it means this decimal expansion will terminate, and it will terminate after 6 decimal places. Next question here we have this 29 divided by 343. We know that we can write this as 29 divided by 7 into 7 into 7, means 29 divided by 7 raised to power 3. So this decimal expansion here in this decimal expansion we can't write Q in the form 2 raised to power n and 2 raised to power m. So it means 5 raised to power m. So it means this decimal expansion is non-terminating repeating. Next question here we have the x is equal to 23 divided by 2 raised to power 3 into 5 raised to power 2. So here we have written Q already in 2 raised to power n multiply by 2 raised to power m form. So it means this decimal expansion is terminating, and after how many decimal places it. So next question we have x is equal to 129 divided by 2 raised to power 2 into 5 raised to power 7 into 7 raised to power 5. Here see I have 7 raised to power 5 also. So it means I cannot write this Q in 2 raised to power n into 5 raised to power m form. So this decimal expansion is non-terminating repeating. Question here we have x is equal to 6 divided by 15. So we can write this as 6 as 3 into 2 and 15 as 3 into 5. This will get cancelled with this, I left with 2 by 5. So it means I can write this as 2 into 2, 5 into 2, means 2 raised to power 2, 2, 1 and 5 raised to power 1. So here I have represented my q in 2 raised to power n into 5 raised to power m form. So it means ninth question, here we have x is equal to 35 divided by 50. So we can write this as 5 into 2 into 5. So it means 35 divided by 2 raised to power 1 and 5 raised to power 2. So here we have represented my q in the form 2 raised to power n and 5 raised to power m. So it means this is a terminating decimal expansion and it will get terminate after 2 places. So last question we have x is equal to 77 divided by 210. So we know that this 77 is equal to 21 into 10, means 77 is equal to 3 into 7 into 2 into 5. So here see we have 3 and 7. So it means we are not able to represent our q in this form 2 raised to power n and 5 raised to power m. So it means this decimal expansion is non-terminating repeating decimal expansion. Next question, second question, here we have write down the decimal expansion of those rational numbers in question 1 above which has terminating decimal expansion. So for that we have to divide them. So we know that from above we know that question 1, 2, 4, 6, 8 and 9 has terminating decimal expansion. So let's see what is their decimal. So now let's find out their decimal expansion by dividing them. First question is x is equal to 13 divided by 3125. So let's divide 13 with this. 13 divided by 3125. So first we will get 0. Here 0 will come, again 0, 0. This is less, again we'll put 0 and like this. So if you divide, you will get, after dividing this, you will get 0.00416. Right, 17 with 8. If we divide 17 with 8, you will get 2.125. I'm not showing all these steps, you can do yourself. Next question we have 15 divided by 1600. So we can write this as 16 into 100. So now you can divide 15 with 16. After dividing this, we will get this number 0.9378 divided by 100. So it means we can put more 2 zeros. It will come like this. So this is my decimal expansion for this number. So here you can get this as 23 divided by 2 raised to power 3 means 8, and this is 25, which is equal to 23 divided by 200. And if you divide these two numbers, 23 divided by 2 into 100, you will get 11.5 divided by 100, which is equal to 0.115. You can do all these steps and please check your answer. And next we have, and if you divide 6 with 15, you will get 0.4. And last question we have, x is equal to 35 divided by 50. If we divide, we know we will get 0.7. Third and the last question here is the following real numbers have decimal expansion as given below. In each case, decide whether they are rational or not. If they are rational and of the form p upon q, what can you say about their prime factors of q? So see here, first question is 4, 3, decimal 1, 2, 3, 4, 5, 6, 7, 8, 9. So see, this decimal expansion is terminating. So this is a rational number. So it means we can write this rational number in this p upon q form. So we can say that this q we can write in the form 2 raised to power n into 5 raised to power m. This is correct. Second question, here we have 0.120, 12000, 12000, 12000, and it will go on. So these type of numbers are irrational. And we know we cannot write irrational number in p upon q form. It means we cannot write this q in the form 2 raised to power n and 5 raised to power m. So last question, here we have 43.123456789 bar. So these type of decimal expansions are rational numbers and we can write them in p upon q form. But here also q we cannot represent in the form 2 raised to power n and 5 raised to power m. With this we have completed chapter number 1, real numbers. So hopefully you enjoyed this video. Thank you everyone for watching my video.